In the last video, we discovered that moving clocks run slower. If you travel fast enough, you age less than people who stay behind. That idea is called time dilation. But there's a problem. If that's all relativity did, it would predict faster than light travel. And that would break the theory. Let's revisit our spaceship. Imagine a star 4 light-years away. A spacecraft leaves Earth traveling at 80% of the speed of light. From Earth's perspective, the math is simple. Earth says the journey takes 5 years. But inside the spaceship, time passes differently. We derived this in the last video. At 80% of light speed, a moving clock runs at about 60% the rate of a stationary one. So while Earth sees 5 years pass, the astronauts experience only about 3. And now we have a problem. If the astronauts traveled for only 3 years, and their ship moved at 80% of light speed, they should only have traveled 2.4 light-years, but the star is 4 light-years away, so how did they get there? Actually, there's an even deeper problem. If the astronauts still measure the distance as 4 light-years, and only 3 years pass for them, they would calculate a speed greater than light, and that would contradict the basic assumptions of relativity. Special relativity started with the idea that everyone must measure the same speed of light. If this calculation is right, the theory breaks. This is the puzzle Einstein faced. He knew the speed couldn't change. We already know time changed. So only one possibility remained: distance. If time becomes smaller, and speed stays fixed, then distance must become smaller too. Einstein's equations leave only one consistent answer. The missing distance never disappeared. The journey itself became shorter. Einstein's equations predict exactly how much the distance changes. From the astronaut's perspective, the star isn't 4 light-years away. It's only 2.4, length contraction, and suddenly the contradiction disappears. The astronauts no longer calculate a speed greater than light. The cosmic speed limit survives. Because space changed. It's tempting to think length contraction is just a correction added to make the math work. But that's not what Einstein discovered. Before Einstein, scientists thought space and time were completely separate. Space was space. Time was time. Einstein's theory revealed that space and time could not be treated as separate things. A few years later, physicists realized they were part of a deeper structure. This is why time dilation and length contraction always come together. When motion changes time, it must also change space. You don't get one without the other. They are two sides of the same phenomenon. They are both consequences of space-time. At everyday speeds, the effect is unbelievably small. A car driving down the highway contracts by less than the width of an atom. But near the speed of light, the effect becomes enormous. You might wonder why we can't simply keep accelerating and exceed the speed of light. As objects approach light speed, relativity becomes more and more extreme. Time dilation grows, length contraction grows, and the energy required keeps increasing. The equations allow you to get closer and closer to light speed, but never cross it. The universe is unimaginably large. The nearest stars are years away even at light speed. Most are much farther. But for travelers moving close to light speed, space itself begins to compress. From the traveler's perspective, the destination gets closer. Relativity does not let you travel faster than light. It does something stranger. It shrinks the road. In the last video, we learned that time can stretch. Today, we learned that space can shrink. And both effects exist for the same reason, so everyone measures the same speed of light. But Einstein wasn't finished. While exploring these ideas, he uncovered another astonishing consequence. A discovery hidden inside the same theory.